All right, so my name is Jamie Duncan. That is a Twitter handle that has lots of stuff about containers and OpenStack and pictures of chickens and babies. That's pretty much what my life is. My title, I don't know what my title is, like this guy, like I've got 4 or 5 of them. I do most of the cloud things for Red Hat. I work with most of our emerging technology portfolio. I specialize most days with our container technology, kind of looking at it from an operations perspective, and then I do a lot of automation with Ansible because I couldn't be sane without Ansible. That's today's date. So this is OpenShift for Operations. I called it OpenShift for Operations because I wanted my talk to get accepted. So I had to have OpenShift in the title somewhere. So let's just take a look. It'll be clear there. I'm an old admin. The container revolution was kind of started on the developer laptop. What we're seeing, though, is the container revolution is being sold to operations teams. They're the people that are taking these systems, these platforms like OpenShift, and they're managing them, and they're tuning them, and they're making them work at scale. And as I go out and I talk to these guys, I run into these questions there. And it's stuff that I assume is kind of common knowledge because my job is to tinker with this stuff all day long. Like, how do you TCP dump a container easily? Raise your hand if you know how to do that. Yeah, right? Okay, so this guy, so he's the smart guy. He's probably a core committer to Docker or something. I just can't see his name badge. And like, how do you easily look at all the processes running inside a container from the host? Again, not hard, but not obvious. So what I want to do today, let's run through about me a little bit. Been at Red Hat for a little over 5 years now. I was at Red Hat TAM for 4 years. Helped start the public sector TAM team. I've been in the sales organization for public sector a little over a year. In that time, I've worked with every major U.S. government agency, including the scary ones. So I have a lot of scar tissue on my back, a lot of miles of bad road. And that is my daughter, Elizabeth. She is the cutest thing ever. That is not negotiable. I mean, seriously, that thing. God, she's cute. She was at swim lessons this morning, and I got video. So I just want to go back to Richmond. All right, so we have a little bit of an agenda. We'll define a task, and that was what I started to do, and I decided to show you guys a picture of my kid. So we have a task, and we always have a few ground rules. We'll talk about how containers are taking over the world. I do have a joke in there that I hope lands, because if it does, it's going to be awesome. We'll talk about deploying an application with OpenShift. So the rest of this deck is under that guise of, we'll deploy an application in OpenShift, which is the most common thing done with OpenShift. And then we're going to take a look at what actually happens. And then we're going to take that application and do a little bit of inspection with it. So we're going to actually take a look and figure out what's going in that container and out of that container. How do I analyze that from the host? And when I can do it from the host, that means I can attach it to monitoring systems and tripwires and all sorts of fun stuff. Then we'll talk about what happens inside OpenShift. Then we'll go down into the kernel because it couldn't be a good geek talk without talking about stuff inside the kernel. Then we'll take a look at how you can't really use OpenShift without understanding, at a high level at least, how the networking works. It's a little not intuitive, so I want to walk through that for a few minutes. And then we'll take a look at how PIDs, process IDs, are isolated inside a container. Because it's not exactly the way we think most of the time. We talk about this process isolation, and there's this large immutable group inside the kernel, and you can't see out of it or into it unless you have these very special things called container runtimes. Yeah, none of that's true. So we'll take a look at reality a little bit, and then we'll have a couple of conclusions. Before we get started, containers are taking over. Can everyone agree with that statement as basic fact? Containers are taking over the world as we know it. Does anyone not have some flavor of container initiative going on right now? Really? Like no containers, nothing. Wow. All right. I did not expect a hand to go up. All right, you got me. You stumped the band. You get a free t-shirt if I had one. This is the world as we know it. Come on, man. It's Settlers of Catan. All right, so the joke didn't land. But it's the world as we know it. We know that, come on, we're super geeks. Let's do that. I think that actually did have the expansion deck in it. I didn't count, but I think it did. So today's task, what we're actually going to be doing, OpenShift, and I know this sounds salesy, and I am technically a sales guy, but it is a statement that I can back up with facts. OpenStack is the most complete production-ready container platform out there. And there are dozens of platforms out there. When you want to drop something in place, use it, scale your application out, thousands of applications, hundreds of nodes of container platform, the one that is proven to do it in production time and again is OpenShift. And there's good reason behind that, and we'll get to that reason here in a little bit. I'll happily have a cold beverage with anyone who disagrees after this session. So if anyone is a giant Docker data center fan or a giant Mesos head, yeah, let's go get a beer and let's figure it out. Because I would love to hear good counterpoints to that statement and heckle you a little bit. So today we're going to take a deeper dive into what exactly is going on when you deploy an application inside OpenShift. I'm firm waiver. So this is kind of the thing. I try to base all of my talks around this idea. Containers are, when we went from physical machines to virtual machines, it wasn't that giant a shift mentally. Sure, there are hypervisors and all of that stuff, but it still looked like a server when I logged into it. The same stuff was in the same place, and my applications went in the same place, and everything was there. It was just virtualized. So IT guys, that was just sort of a migration. Then containers happened, and they feel weird. When I walk in the door and I tell a customer that we're going to stand up 20 nodes of this thing, and I'm going to drop your application onto 10 of them, and it's going to be any number of those 20 servers, and it's going to vary from time to time, and you're not even going to know the IP address that it has at any time, you're just going to magically map this thing out, and this thing called Kubernetes will just do it for you? I get laughed at. Not so much now, but back then they're like, yeah, you're an idiot. No, you're not going to do that, is what it feels weird to an ops guy. You can't go put your hands on it. You can't go look in vSphere and say, this app is these 3 machines. Here's my database. It's going to float around out in this ether that is a container platform. So you got to have a firm grasp on the basics of what they're doing. And I'm not talking, we're not going to go look at code written in Go or down at the namespace code in the kernel. That could kill us all. But just a firm concept of what's going on inside a container. We always have a few ground rules. And these ground rules are more for my benefit than yours. But this is a discussion, not a lecture. Me standing up here for the next 40 minutes and talking will be boring for me and for you. Have opinions, voice them. There's a very good chance you know something that I don't know. It's a discussion, not a lecture. The information in this deck is accurate to the best of my ability as of OpenShift 3.5. No technology is moving faster than containers. I have literally given a container talk, looked at the deck the night before, and something was substantively different the next day when I actually delivered the presentation, and I got called out on it. So it is accurate as of about a day and a half ago. It's accurate as of the horrible go-go internet on my flight from Richmond. It was accurate. So, and this is a nuts and bolts talk. I'm a nuts and bolts guy. I like to see how things work, and I like to show and help people understand that. We're not talking about roadmaps, and there are no change logs in here. So if you want a roadmap talk, I don't know who they are, but I'm sure there's a different session. And at the end of the day, it's all about getting some new information and having a couple of laughs, I hope. The Catan joke didn't land, but I'll work on it. There's another joke cooked in here, and I hope that one fares better. All right, so to start out this sort of demo-driven idea, the first thing we do is type in OC new app. And whether you go through the command line or you go through the web interface for OpenShift, this is how you build out an application. OC is the command line client for OpenShift. OC new app, you give it a name, you tell it some code that you want to use. In this case, it's some little silly application that I wrote for a project I'm working on. And then I tell it that I want that to be a PHP app. That's all I got to tell OpenShift. OpenShift takes my code, makes it magic happen in the middle, the gears turn, and seconds or minutes later, depending on where I'm at in the Wi-Fi world, my application's up and running. Some people have done this. You guys okay with this idea? I feed it code, I tell it what the code is, magic, I have a URL to go look at my code. So that's where we're going to start. We have deployed, let's assume, in my cluster running on my laptop, and we can pull it out after the talk if you want. That works. So raise your hand if it looks familiar. So let's connect the dots a little bit. What actually happens in those intervening seconds and minutes? There are no voodoo chants. We don't have Cupid dolls to actually inflict harm or magic on a server. So OpenShift does some things on its own. And this is the code that Red Hat has written that sits on top of Kubernetes. So OpenShift takes and builds out a custom container image, takes your source code, takes what we call a builder image, marries the two together, and then creates a custom container image just for your app and stores it in its internal registry. So we do that. So now we have a container image for our app that we're going to deploy. It creates a thing called an image stream that ties all of these other resources together. It says, my image stream says, all right, this is the name of my app. This is the place, these are the image I'm going to use for it. Here's how many replicas I want. It takes all of the information that I want for an application, and we start populating this image stream. I build a thing called a build config, and I tie that into my image stream. And the build config defines how my app is built. So I say, I'm going to take this image. I need to mount these persistent volumes into it. I need to grab this from the host. I need to go download this SQL file. I need to do whatever I need to do to build my application, to create this custom container image. And that's associated with my image stream. Then I create a thing called a deployment config. The deployment config tells OpenShift how my app's going to be deployed. So it's going to say, here's the build, here's the image, and then I want you to deploy 10 of these things, and I want the pod to be named this, and I want the containers to be named that. And when you upgrade down the road, I want you to use a rolling upgrade method, or I want you to use a blue-green or a canary method to actually update this application. So I'm building out all of these facts about this image, and all this is happening in those seconds or minutes while my app is deploying inside OpenShift. And the deployment config is kept track of by the image stream. The image stream is my source of truth for everything. Then I also update a load balancer configuration, because I'm going to eventually have a URL to go to get to this thing. OpenShift runs HA proxy internally, or it can actually hook into like F5 big IP load balancers. So I update those configurations with a URL to point to my application. So I have HA proxy running inside OpenShift that's going to point it all to the right place once it's all built, and that's recorded inside my image stream as well. Then OpenShift talks to Kubernetes. So OpenShift's done all this on its own. Then OpenShift tells Kubernetes to go do some stuff. Kubernetes builds a replication controller. The replication controller is the Kubernetes thing that says, thou shalt always have 10 of these container images running. And when I tell it, no, I only want 5, then the replication controller scales down those 5 or scales it up to 500 or does whatever I need it to do. So Kubernetes creates that object inside the Kubernetes database. It also creates a thing called a service that is a single endpoint that can direct traffic to all of those pods inside that replication controller, all of those containers inside the replication controller. Then Kubernetes talks to Docker. Jesus, this is long. Kubernetes talks to Docker to actually create, we haven't even built a container yet. All we have is a container image and a bunch of YAML at this point. So now Kubernetes actually talks to Docker, the container runtime, to create the containers to put in this new replication controller that Kubernetes just created. And that moves us down into the kernel. Because then we have to think, what is a container? Can anyone tell me can anyone want to take a stab at answering before I hit the button a few times? Come on, somebody. Remember, discussion, not lecture. What is it? Okay. Yeah. You forgot one. Well, there's the process of an SE Linux is the last one. Ah, stupid SE Linux, that thing we disable. So, so then Docker, what Docker does is manage a bunch, and he just named most of them, and I'm not going to repeat them because I'm going to repeat them over the course of this slide. But he was almost 100% right. So then Docker interfaces with the Linux kernel. And the Linux kernel, we build out a bunch of things to help isolate this process that we're about to start. We tell our custom container image, we take this custom container image and we take any kind of mount points that we defined in our build config and our deployment config and our image stream, and we mount in all of these mount points, so a shared storage or a host directory from the actual host or whatever we need, we put them in what's called a mount namespace inside the kernel. And that mount namespace makes that chunk of the file system feel like it's isolated. It can't see anything else on the host. We can see into it, it can't see out of it. So my application's file system feels like it's isolated. That's why every container can have its own temp directory and its own /etc and its own set of libraries. That's all possible because of the mount namespace. So that voodoo magic, no, it's just a mount namespace. We create a network interface, and we isolate that network interface with what's called a network namespace. The network namespace does the same thing, but for the networking stack. So all of the networking traffic, we create a set of ring buffers in the kernel for IP traffic coming in and going out. We create our own MAC address, create our own IP address that Kubernetes tracks for us. All of it's isolated. To the applications running inside this container, it feels like it has its own isolated network stack. And we're going to get a little deeper into what that actually does here in just a couple of minutes. Then we isolate the memory resources. Because if I've got 2 copies of a Java app running, and that Java app, both of them try to create the same name semaphore, or the same shared memory resource, I get a big fat seg fault and my application dies. We use an IPC namespace, inter-process communication, so we can cordon off chunks of RAM and have multiple shared memory resources with the same name running on the same server. So we don't get seg faults, everything just works happily. So again, just kernel files, kernel tricks, things that have existed in the kernel for years. The IPC namespace showed up 2010, 2011. It's been around for years. We just haven't been leveraging it very well. Then each container gets its own hostname and domain name. And we use what's called the Unix time sharing namespace for that. I really had to dig in to figure out why it's called Unix time sharing. There's actually and this is probably the dorkiest moment of the 45 minutes I'm up here. There's a data structure inside the kernel that keeps track of your host name and the time zone you're in and a bunch of other stuff. It's called the UTS data space. Well, that's also why uname, like if you look at the kernel release you're running, like uname-R, uname-A, the U is because it's hitting that same chunk of data inside the kernel. That's why this is called, so my own host name and domain name, because if I've got 500 containers running on a box, or I have an application running in 50 containers stretched across 100 servers, figuring out the host name if one's acting funny is going to really help me in troubleshooting and forensic analysis. Then I give my container its own set of PIDs. The application I use to launch a container, inside the container it looks like PID1. So PID1's not init inside the container. If I'm starting Apache to run a PHP app, which is what this example is, and we'll look at it here in depth in just a few minutes, HTTPD is PID1. Like when I first started looking at containers 3 or 4 years ago, I was like mind blown. Like PID1's important in the Linux world. PID1 is init. PID1 is the thing that starts all the other things, except in a container. PID1 is just the process you're running. So every container gets its own set of PID counters. And Docker is creating all of these resources for us and putting our application in them when it launches it on the fly. This is what a container actually is. Then the Docker also tells Linux to create kernel control groups. Anybody using kernel control groups a lot? Like, what are y'all using them for? Nice, awesome. I used it to keep Java from eating the world. That was my primary use case. Right. So nothing can fix bad code, but I could put Java apps in a C group, in a control group, and it would consume all of those resources and eat itself, and I'd have to restart the service, but I wouldn't have to restart the server. So C groups are quotas enforced by the kernel that you can put per process ID on a system. And you can enforce quota on all of the I/O coming into a kernel. Disk I/O, network I/O, CPU cycles, and RAM access. So I can throttle data, so I get rid of noisy neighbor syndrome with containers inside using kernel control groups. And Docker creates those on the fly for me in milliseconds. And the other thing the container runtime does is create unique SE/Linux contexts for each container. I'm going to ask a question and everyone raise your hand or I'm going to get really angry. Who is running their systems with SE/Linux enforcing? Who's lying? This guy. All right, you had a free t-shirt. You don't have it anymore. SE/Linux is a labeling system that's cooked into the kernel that lives below file system attributes that we usually associate with ownership. It's a labeling system. So I can do things with SE/Linux like tell the Apache executable that it can only read Apache config files with the Apache config label, and it can only write into directories with the Apache read-write directory label. I can restrict incredibly fine-grained controls with SE Linux. With containers, every container gets a unique SE Linux context. So even if I somehow manipulate code to get from my container to the host or the container to another container, I'm going to go into that space with the SE Linux context of the original container, and I can't do anything. I'm in a complete, I'm root on the host, and I can't even write to /temp. And that's what SE Linux does for us in the container space. And it actually does the same things with virtual machines with a thing called svert. So we create unique SE Linux contexts for every new container that we create. So all of that text, let's look at it. I'm going to say it all very fast again in an infographic-y kind of way. We have OpenShift. OpenShift creates a container image for us, creates an image stream for us to associate all of this information, creates a build config for us to build our app, creates a deployment config to deploy our app and upgrade our app. It creates an HA proxy configuration so traffic gets in and out cleanly and I don't have to mess with IP addresses inside Kubernetes. Then it talks to kube itself. Kube is shorthand for Kubernetes, or Kates. Kubernetes creates a replication controller which tells me how many of these types of containers I want to keep running at all times. It also creates a service that gives me one place to go to talk to all of those containers. And Kubernetes will route traffic. No matter what host it's on, that service knows where all these endpoints are. Then we get to Docker. Docker creates a mount namespace for our file system isolation, creates a network namespace for our network isolation, creates an IPC namespace for our shared memory isolation, creates a UTS namespace for our unique host name and domain name, and then it creates a PID namespace, so all of the process IDs inside our container are unique to that container. So PIDs get pretty important, and being able to just say kill PID 500 and kill PID 500 in every container is a bad thing, and the PID namespace stops us from being able to do that. And then on top of, notice we're all built on the bedrock that is Red Hat Enterprise Linux. Docker then talks to Linux, and these resources are shared. There's only one SE Linux. There's only one C groups. So we create C group SE Linux contexts to keep our container isolated effectively on the host. And then we create control groups to effectively isolate our containers' resources to make sure we don't run into noisy neighbor syndrome. To make sure one container can't suck in all the resources and drag any other containers or on the host. Make sure they can't drag them down. Does all that make sense? I kind of hit you guys with a fire hose for about 20 minutes. This is also known as a modern container platform. Checkbox. That's what we're doing. So even if you take off all of the cool stuff with OpenShift and Kubernetes, it's all the Linux kernel. All of those things that isolate one container from another, that make my application in a container feel like it's sitting by itself, even though it's sitting with dozens or hundreds of friends on the same host, it's all dug deep down into the Linux kernel. We're talking about deep, dark Linux code here, folks. It's not DevOpsy. This is super geek. All right, so for an ops team, and this is kind of the question that I was posed when I decided to put this in. For an ops team, how do you manage all of this? Right, because I've got Tripwire and Nessus and security scans and PCI compliance to deal with, and God knows what. How do I apply all that to a container? I guarantee you Nessus has no concept of a namespace. So let's start with what everyone always says is the hardest. When people start talking about emerging technology and they ask about networking and OpenShift or OpenStack, my answer is, yeah, it's hard. That's all I ever say, and then I try to go to the next thing. But let's start with networking. Let's just jump at the gorilla. And also, please note the Linux beard. So you can tell this is an ops guy. This is no developer. Bald, beard, Linux guy. That's all you need to know. So OpenShift networking. OpenShift uses software-defined networking to isolate resources better inside the cluster. And software-defined networking can be a little scary, but it's actually not that weird. So let's say we have 2 containers up and running. Each of those containers has that interface that was created by the network namespace. So I have 2 containers, each one has an E0. I have on the host a corresponding, what we call a vEth, a virtual ETH, that is linked through the kernel, and we're actually going to look at this in depth here in just a few minutes, linked to the kernel. So I have a one-to-one mapping of this veth to eth, and for each container I have a corresponding veth device. And there's a problem there, but we'll solve it. Each of those virtual Ethernet devices lives in an OpenVSwitch bridge. This isn't a Linux bridge, it's an OpenVSwitch bridge, which makes it fancier. But they do essentially the same thing. They take all of these different connections, they take all these different interfaces, and they let them share other resources, let them route traffic more efficiently to one another. So there's always a bridge 0 on an OpenShift host, and that bridge 0 contains all of our virtual interface devices that are our container NICs, our container interfaces. Then if I need to get traffic to somewhere else on my OpenShift cluster, that traffic is routed through a VXLAN, so in an encrypted VXLAN tunnel. And the way you can design OpenShift, everyone can use one, or each project in OpenShift can have its own VXLAN. And I can actually isolate project network traffic at the project level. So I can get really fancy with the way I isolate traffic inside my OpenShift cluster. And then if I need to get out to the interwebs, which is, we all know, a series of tubes, there's a tunnel device, an old, TUN-TAP interface, is also attached to that bridge, and it's routed out the front door of the server to get out to the wider world through whatever the default gateway is. So this is exactly what networking looks like inside OpenShift. So I have, each container gets a NIC. Each NIC is mapped to a NIC at the host's network namespace. Then to get out to my OpenShift cluster, I go through an encrypted VXLAN, encrypted end-to-end. And then to get out to the world, I go through a tunnel interface, which is just routed out through whatever my default gateway is, or whatever my routing needs to be for my infrastructure setup. Everyone cool with this? This is pretty straightforward. This is how most software-defined networking works. It's all just VXLANs and tunnel interfaces. Seeing this in action, OVS VCTL, this is on an OpenShift cluster. OVS VSCTL, not the easiest thing to say or type, but that's the OpenVSwitch vSwitch control program. I can actually list the bridges, and I get BR0. So I have one bridge here. And then I can also list the interfaces in BR0, and you can also see where right here I have a brain fart, and then I keep typing. And there's TUN0, VXLAN 0, and my 3 VEs. Well, let me, and I keep going. So you see the problem is those numbers, those hashes for those VEth devices are created by OpenVSwitch, not by Kubernetes. There's no easy mapping. I can't say, oh, this hash matches out to a hash in Docker or a hash in Kube or a hash in OpenShift. So there's no intuitive correlation there. But there is a correlation there. But now how do we figure out? So if I wanted to do a TCP dump, and everyone has to do a TCP dump from time to time, need to do some sort of packet inspection or grab a header or see if I'm getting retrans or something, I could just TCP dump the VEth interface on the host and see everything coming and going from my container. But how do I know which one? Well, I said they're linked inside the kernel, and that's a completely accurate statement. If you go look at the kernel man page, which I do not encourage anyone to do, there's actually an if link value, and if I can link one interface to another interface at the kernel level by setting this value, and I'm actually showing this here. So I can do an OC get pods and grab the app we deployed earlier. This was an honest demo. I did do the exact same thing. This was on the same system. I can grab this pod name, and the pod is just my replication controller. It's just my app. Then I OC execute, so I can execute a command inside that container, and I cat out a file from /sys. In this case, sys class net eth0 if link. This if link, and I got a value back of 23. Well, then if I look back on my host, and you see I actually SSH'd into my host where this container was running. If I look at the output of IP address show or IP all, you know those little numbers that no one ever figured out what they were running down the left-hand side of that interface, that's your interface number. So that if link value inside the container is the interface that my traffic is going in and to out on the host. So here I got 23 in my container, So that vETH, that virtual ETH, number 23, is what all of the traffic going in and out of that container goes in and out on. So I don't have to go into the container and do some weird third-party crap. I just do a TCP dump of that thing. I have to cat one file in the container, and then I have the interface I need to look at all the traffic coming and going from that container on the host. And I got to be root to do all that, but it's there. Everyone cool with that? So now everyone in this room can TCP dump a container in about 7 seconds. You cat out one file in the container, and you know which interface you're associated with.
Sometimes you might still need to look at traffic totally inside the container.
Maybe. I can't come up with a scenario unless the kernel itself was corrupting data. This is linked at the kernel level. So if it goes into the virtual ETH, they're essentially the same thing. They're carbon copies of one another. They're just in a different network namespace. So they just can't see each other easily. And so unless the kernel itself was doing something bad.
Something like interface MPU or something like that.
Maybe. Yeah, I'd have to test it. I'd want to watch it on both sides. But for the vast majority of troubleshooting traffic, and I just have it, that may be the same. I'd have to actually test it. So that's how you TCP dump a container. Ops guys have to do that stuff every day. That's kind of what we do for a living. Go do some packet inspection. Go see if I'm getting retrans. Go see if the Apache headers are actually making it through, because I can't see them through all of my troubleshooting tools. And the next thing that I wanted to show, and we started at 3:30, so we got about 15 minutes left, right? We got about 15 minutes. So 5 or 10 minutes, that'll give us 5 or 10 minutes for just a complete wide open Q&A. The other thing is, how do I look at the host? I want to be able to see what processes are running in a container from the host. And this could be good for something like, I don't know, monitoring applications, good for any kind of CI/CD workflow. I could actually kill a process inside from the host in the container. If I couldn't, say if Docker wasn't responding correctly, or I couldn't get in the container for some reason, say I didn't have a bash executable in the container, then I can't create a shell in the container. So there are all sorts of scenarios excuse me, where I need to do something to the container, to a PID, a process in the container, but I can't get in there to do it. I can't get into that namespace. Well, I can do it from the host as well. So here, I'm actually using Docker, and we'll let it restart again. So I'm actually using Docker PS to show me all the containers that are running, and I just grepped for the one that I deployed. And then that unique ID is Docker specific, and I can actually use Docker inspect and just get out the PID that I'm looking for. And that -F is just, I'm just looking for a subset of the data coming out of Docker inspect. I just didn't want it to scroll for 10 years on this graphic. So Docker inspect, and I see that I've got PID number, almost had it timed, 4218. So that container, PID 1 in that container, that process that launched my container that I was talking about earlier, is actually, on the host, is actually PID 4218. And then I can look and see what other processes that PID, that process ID, has spawned. I can just do a simple PS tree, or just PS and grep and look for whatever. So PS tree -PID 4218, and I see here, it's Apache, just like I promised. And then it had spawned some child processes. Does that make sense to everybody? So I'm just asking Docker for a PID, and I'm feeding that PID into PS tree. But then when I look at the container, we'll see the output one more time. It's not exposed in the OpenShift metrics tooling, not by default. I mean, I'm on an OpenShift cluster, but this is ops command line tooling. I'm logged in as root. So this kind of scenario is troubleshooting something that's not acting right in OpenShift. So if an application's acting improperly, or something just doesn't feel right for an ops guy, if your trick knee is kicked in, and we all have that. I always say, it just doesn't smell right. Then we can go in and start inspecting stuff. This is completely out of band to OpenShift management. So this is what someone with root access to the OpenShift cluster could do. This isn't available to anyone. And then if we look at the container itself, and instead of using OC exec here, I just decided to use Docker exec because they're under the covers, they're the same thing. I execute a bash shell inside my container. I then make sure that I have a different host name just to prove I'm in a container. And then I have the exact same output that I got from PSTree, only now, instead of PID 4218, HTTPD is PID 1. So namespaces aren't these crazy immutable brick walls inside the kernel, they're two-way mirrors. I can leverage the operating system if I have the right level of privilege to see in the container from the host. I can't see from the container out into the host. I can go from the host in, I can't go from the container out. That's what namespaces, that's what containers let us do. It's just process isolation. There's no magic voodoo, there's nothing. Does everyone make sense with that? Does that make sense to everybody? They're just another tool for operations to use. They're the next layer of density. You know, so everyone here I'm sure is very heavily virtualized, and this is kind of a non sequitur. Who's got an average utilization on their virtual server cluster north of 20%? You're the best person I've ever seen, you're best at your job I've ever seen. Do what? Okay. So we had a ton of physical systems sitting at 3% utilization, and then we P2V'd the world, and now we have a ton of, but we never lost that idea of worst case scenario provisioning. We over provision our VMs consistently because we have to build them for the worst day. Because they're not, it takes minutes or sometimes hours to scale them up properly. Containers I can scale up in milliseconds, so I can right size a container much faster, much more easily. So what we see out in the world is miles and miles and miles of VMware, and the average VM is sitting at 5% utilization all the time if you're lucky. So we're still just wasting resources. But now I can take something like OpenShift, drop dozens or hundreds of containers on each host, and I can effectively utilize an OpenShift host if I'm good, 70, 80, 90% consistently. I can sweat my hardware more. Who's got a bigger budget next year than this year? Really? Where do you work? I want to give you my resume. A bank? All right, maybe. Yeah. All right, he's probably telling the truth. One hand went up out of a room of, 100 people. 2 hands went up. Are you working at a bank? Yeah, 2 guys work at a bank. Wow, all right. Wouldn't have picked that one. But the vast majority of people, who's got more responsibility next year than this year? So almost everyone's hand went up, and the rest of you just didn't want to admit it. So out of 100 people, everyone has more work to do, and 2% of you, plus or minus, have more budget to do it with. You got to sweat your hardware more. You got to automate everything. That's the only way you survive. I'm able to do all of this stuff we just talked about, create all this magical YAML, deploy all these applications across all these servers, and then actually go and inspect them pretty effectively and pretty easily using traditional tools. I'm catting a file and using PSTree. I mean, I didn't, nothing, stuff we use every day. So I'm able to use traditional tooling to inspect containers a lot and to really get that information and make them feel like a regular part of my operations. But I'm able to sweat my hardware more effectively because containers afford more density. I can have 50 port 80s on a single host. I'm a firm believer 80% of the virtual machines exist because someone needed another port 80. Pretty sure that's fact. Don't have hard data on it, but I'm pretty sure. We don't have to do that anymore. We don't have to isolate processes with virtual machines. We can isolate processes with containers, and we get more effective use of our hardware. We can shrink, 100 VMs down to 10 or 12 using containers with most customers. And we can do it effectively, and we can do it with an immeasurable loss of performance. Containers add 1%, maybe, to latency. All of those things inside the kernel are incredibly fast, and they spawn up in milliseconds. It's kind of rolling through a couple of conclusions. OpenShift automates a lot of the work to make applications elastic. We have to have all that YAML. We have to have build configs and deployment configs and image streams and replication controllers and namespaces and all that stuff. OpenShift automates it for you. If you decide to do like a roll your own Kubernetes, you got to figure out how to do all that crap. And maybe you're as smart as Google. I don't know. Well, these two guys have more budget to throw at it. But I'm not. I couldn't invent Kubernetes tomorrow. I couldn't reverse engineer it in 2 years, 3 years. So OpenShift automates all of that stuff using open source hardware. For an ops team, you have to think about applications differently inside OpenShift. But you can analyze them with traditional tooling. And you can take that traditional tooling and make that the first step to getting it effectively into your monitoring applications, getting them effectively into your change management controls, getting them effectively into your mainstream ops pipeline. You don't have to treat containers like unicorns anymore. OpenShift ships with a lot of the tools to get the information you need. It's Linux. We're just manipulating Linux a little differently. Nowhere in a diagram or screen capture did I reference voodoo or unicorn blood. There is no magic in containers. Containers do not equal magic. It's just Linux. Containers equal more effective process isolation. And just to drive it home, most importantly, in my humble opinion, containers equal Linux. And then you're at Red Hat Summit, so I'm going to go ahead and say it, Linux equals RHEL. That's it. I don't care what marketing people for any other company say, that's it. Containers are Linux. We're leveraging Linux in a new way. That's it. So we have 5 minutes. Anybody want to call me an idiot on tape? Please feel free. Go for it. So the question was a little bit more on how the physical resources are isolated. And the tool there, the tool in that toolbox we talked about is control groups. So when I create a control group, I can associate it with, in the wider world, I can associate it with a user or a group or a process ID. With containers, we're associating with a process ID. So when Docker is creating a container, when the container runtime is spawning a new container, it's also putting those applications in a C group. And that C group, I can limit the number of CPU cycles. I can limit the number of cores it has available to it. I can set a specific core available to it. I can limit the amount of RAM it has total. I can limit the IOPS per second to memory, and I can limit the IOPS per second to disk and network. So that's how we're sandboxing the physical resources per container.
And where are those things declared?
There's inside, if inside the C group module in the kernel. So in the world of OpenShift, you declare all of that in your build config. So there are options to say, I want to limit this container. You can set defaults. You can set defaults per project. And then if you have something that's a one-off inside a project, you can actually declare them independently in a build config and limit your resources that way. So the question was, if I've scaled my applications dynamically up to the limits of my application platform, can I dynamically scale my application platform? The short answer there is no. OpenShift doesn't have a mechanism inside of itself to build out a new node. The install tool, which is just an Ansible playbook under the covers, you can add a new node to the cluster in a pretty trivial fashion. The way I see people, when people are doing it really well and really awesome, you have these sort of axes of scalability. I have an elastically scalable application, and that platform, my application platform, lives on an elastically scalable infrastructure like OpenStack, or like a traditional virtualization platform like VMware or Red Hat virtualization, controlled by something like CloudForms. OpenShift on OpenStack is the sexiest thing you've ever seen, because then you can actually set auto-scaling of the cluster and automate all of those steps to add a new host to the cluster, and it just goes up and down on its own. It's some pretty cool stuff. But inside OpenShift, we figured it was going to be hard enough to scale the app. We didn't want to try to glue in code to scale itself, because you can run it anywhere you can run RHEL, and then we're just writing a big fat hack at that point, because you can run RHEL pretty much anywhere. I mean, Red Hat Linux is running on Mars, for God's sake. Not a new enough kernel to run containers, but the kernel's a little out of date on the rover, but it is the Red Hat kernel. Any other questions? We have just a couple of minutes before they kick us out. Any other thoughts, questions, concerns? Anyone who want to buy me a beer and tell me there's a better platform? It is. In fact, there will soon be an RFE. I literally 2 days ago, we did a lab on Tuesday, and a guy from Penn State comes up and says, this information needs to be easier to get at. And yes, you're exactly right. Right now, I can figure out where that endpoint is with I cheated here and had a 2-node OpenShift cluster. So I cheated a little. I did the infomercial. I put the raw turkey in and pulled the cooked turkey out. But yeah, so there would, if to do a multi-node setup, I could figure out which, that pod, OC get pods, and it'll tell me all the different pods running for an app, and it's mapped to a host there. So I did skip a step by running a single node, and that may be exactly what, I sent an email out to some of our engineering and to that customer, maybe last night about 1 a.m., saying that exact thing, that we need to make in particular, the command line client in OpenShift a little more operator friendly, ops friendly, and this kind of, cooking that kind of thing into it would be a great first step and be a pretty low lift. So I think we're right up on time. If anybody wants to chat outside afterwards, I'm happy to, but that's what I got. Thanks a lot.